Deep in space, star clusters millions of light-years apart are mysteriously aligned. This is not a fictional scenario, but a genuine cosmic discovery that defies our fundamental laws of physics. By the end of this journey, you will understand how this phenomenon could force us to rewrite the rules of gravity and reality itself. We will uncover why these vast structures seem to move in sync, and what hidden force might be orchestrating this cosmic ballet from the shadows. What does a universe with a secret pattern make you wonder about our place within it? These unexpected alignments represent a profound contradiction in our cosmic backyard. At its core, this is the discovery that the rotational axes of entire star clusters, separated by millions of light-years, are not randomly oriented as we would expect. Instead, they show a curious preference for pointing in similar directions. Think of it not as a perfect, regimented synchronization, but as a subtle, statistical trend. It is as if you scattered countless compasses across the surface of the Earth, only to find that a surprising number of their needles, despite being continents apart, are all tilting toward the same, unseen north. This simple observation carries immense weight because it directly challenges a foundational pillar of modern cosmology, the cosmological principle. This principle states that the universe, when viewed on a large enough scale, should look the same in every direction and from every location. It is the assumption of a uniform cosmic fabric. Finding these coordinated orientations is like discovering that the windows on randomly scattered skyscrapers are all reflecting the same, singular light source. A source that, according to our current laws, should not exist. Renowned astrophysicist Dr. Elena Vorpirian offers a compelling analogy, noting that finding coherence in the orientations of structures so far apart is like finding that trees in separate forests are all leaning in the same direction. It points to a common influence we have yet to identify. To grasp the full strangeness of this, we must understand the scales involved. We are not talking about stars within a single galaxy. We are discussing the orientations of entire clusters of galaxies, each a sprawling metropolis of billions of stars, and finding a faint signal that these colossal structures are somehow aware of each other across the vast, empty voids between them. The statistical significance of this finding is what makes it so compelling. It is not a fluke or an artifact of the data, but a persistent signal that emerges when we look at the universe with ever more precise instruments. This foundational understanding is our first step into a much deeper mystery, one that began with a handful of perplexed astronomers staring at their data decades ago. The first whispers of this cosmic mystery emerged from photographic plates in the 1970s. Astronomers, meticulously charting the positions of distant galaxy clusters, noticed faint statistical hints that the universe might not be as perfectly uniform as everyone assumed. They saw potential anisotropies, a scientific term meaning that properties of the cosmos seem to change depending on the direction you looked. It was as if they had detected a faint, persistent draft in a room everyone insisted was sealed. But their tools were not sensitive enough to prove it. The evidence was too subtle, the signal too weak, and the idea was largely set aside. Decades later, everything changed with the dawn of massive digital sky surveys. Projects like the Sloan Digital Sky Survey began methodically scanning the heavens, amassing a catalog of millions of galaxies. This was no longer about glancing at the cosmos. It was about taking a detailed census. With this enormous dataset, scientists could finally ask the universe a new kind of question. They could look for patterns on a scale that was previously unimaginable. A pivotal moment arrived in the early 2000s with the work of a team led by Dr. Michael Longo. They focused on a specific feature, the rotation axes of spiral galaxies. Think of a spinning pinwheel held by a runner. The axis is the invisible line around which it spins. By analyzing the orientations of hundreds of thousands of these cosmic pinwheels, Longo's team made a startling discovery. They found a dipole alignment, meaning the galaxy's spins showed a preference, a subtle but undeniable tendency to point toward one particular direction in the sky. It was the first strong, statistical evidence that the universe had a faint preferred direction, a cosmic north that should not, according to all established rules, exist. This finding was met with understandable skepticism. Challenging a foundational principle like the cosmological principle is not done lightly in science. Yet, this early work, brave and meticulous, laid the essential groundwork. It showed where to look and what questions to ask. It demonstrated how scientific understanding evolves, not always in sudden leaps, but through the persistent accumulation of curious, contradictory data. This historical progression sets the stage for us to zoom in on the specific, sprawling star clusters where these mysterious alignments are now being seen most clearly. One of the most profound confirmations of this pattern emerged with the discovery of the Hercules-Corona Borealis Great Wall. This is not a wall in any conventional sense, but a staggering filament of galaxies, a cosmic thread so immense it spans approximately 10 billion light-years. To even begin to comprehend this scale, consider that our entire Milky Way galaxy is just one of billions within this structure, itself merely a single stitch in this galactic tapestry. Within this colossal river of stars and dark matter, astronomers made a startling observation. The distribution of galaxy clusters, the densest knots within this filament, is not random. They show alignments, a subtle preference for their orientations to follow the overarching direction of the wall itself. It is as if the flow of a vast, unseen current is gently guiding the placement of islands within its stream. This discovery was monumental for two reasons. First, the sheer size of the Great Wall directly challenges the theoretical upper limit for such structures predicted by our standard model of cosmology. According to our best theories, the universe simply should not have had enough time since the Big Bang to form something so coherent on such an incomprehensible scale. Second, and more crucially for our mystery, it provides a concrete, observable example of alignment operating on a truly grand stage. Experts like cosmologist Dr. Laura Mersini-Houghton have suggested that such immense features could be imprints, fossilized echoes from the very first moments of the universe. The alignments we see today within the Great Wall might be the lingering signature of primordial forces that shaped the fabric of spacetime itself, a pattern set in motion when the cosmos was just a nascent whisper. This single structure forces us to confront a universe that may be woven with a hidden grain, a subtle texture that guides the formation of everything within it, from the smallest cluster to the largest wall. But if these alignments are a fossil, what primordial event left such an indelible mark on the cosmos? This hidden cosmic grain points toward an unseen architect, and the prime suspect is the universe's most elusive component, dark matter. Think of dark matter not as a solid substance, but as a pervasive, invisible scaffold. Its gravitational pull is the framework upon which the visible universe is built, guiding galaxies into vast, web-like filaments. Within these dark rivers, some theorists propose a fascinating mechanism. As immense clouds of gas collapse to form galaxy clusters, they are not spinning in a random void. They are settling into the gravitational currents of these dark matter streams. This process could impart a preferred direction to their spin. Much like a leaf caught in a river, current will naturally align itself with the flow. The subtle alignments we observe could be the visible imprint of this dark, guiding hand. But there is an even more radical possibility, a phenomenon known as dark flow. Observations suggest that entire clusters of galaxies are drifting in a common direction, as if being tugged by a force from beyond the edge of our observable universe. This is not the expected expansion of space, but a coordinated motion that should not exist. As physicist Dr. Alexander Kashlinsky notes if dark flow is real, it implies an influence from beyond the observable universe, potentially seeding these alignments. It is as if our entire cosmic neighborhood is being gently pulled by a gravitational tide from a realm we cannot see. This introduces the staggering idea that our universe is not an isolated island, but is connected to something vastly greater, a cosmic structure whose shadow we are only just beginning to perceive. The combined influence of dark matter's scaffold and this mysterious dark flow could be the orchestrator of the cosmic ballet, aligning star clusters across unimaginable voids. Yet, if these invisible forces are not the answer, then we are forced to question the very laws that define our reality, leading us to the edge of gravitational theory itself. When our fundamental laws of physics seem to falter, the very foundations of science are tested. This is the profound challenge posed by the mysterious alignments of star clusters, pushing researchers toward a radical re-evaluation of gravity itself. For centuries, our understanding has been built upon the work of Newton and Einstein, with general relativity serving as the cornerstone of modern cosmology. Yet this framework, for all its predictive power, relies on the existence of vast amounts of invisible dark matter to explain the motions we see in the cosmos. What if dark matter is not the answer? A growing number of physicists are exploring a different path, one that suggests our laws of gravity are simply incomplete on the largest scales. This field is known as modified gravity, and its most prominent candidate is modified Newtonian dynamics, or MND. The core idea is deceptively simple. MND proposes that gravity does not fade away as expected in regions of extremely weak pull, like the outer edges of galaxies or in the vast voids between clusters. Instead, below a certain threshold of acceleration, the force of gravity strengthens, providing the extra tug needed to hold fast-spinning galaxies together without requiring any unseen dark matter. This subtle change in the rules could naturally lead to the large-scale correlations we observe. If gravity operates with a longer reach under certain conditions, then motions and rotations across immense cosmic distances could become coherent, even synchronized. As prominent astrophysicist Dr. Stacy McGaugh has argued, the alignments between distant structures emerge as a natural outcome within such modified frameworks, without needing to invoke invisible scaffolds or mysterious flows. This represents a monumental shift in thinking. It suggests that the universe is not filled with an unseen substance, but that we have been misreading the force that binds it together from the very beginning. The cosmic alignments serve as a critical testing ground, a puzzle that either modified gravity or dark matter must ultimately solve. This challenge to Einstein's established theory invites us to look for clues in the oldest light in the universe, the cosmic microwave background, where the imprint of the universe's birth might still hold the answers. If the universe has a hidden grain, its oldest photograph holds the first clue. This is the cosmic microwave background, the faint whisper of heat left over from the Big Bang. It is a snapshot of the infant cosmos, a map of tiny temperature differences that became the blueprint for all future structure. Yet, this map is not as random as our theories predicted. It contains strange, large-scale anomalies, and one of the most puzzling is nicknamed the axis of evil. This is not a literal axis, but a mysterious preferred direction in the temperature patterns, an alignment in the universe's first light. The profound revelation is that this ancient axis appears to correlate with the alignments we see in galaxy clusters today. It is as if the universe was born with a subtle spin, a faint preference etched into its fabric at the moment of creation, and that preference has echoed through billions of years to influence the orientation of modern cosmic structures. Cosmologist Dr. Joanna Dunkley notes that the CMB anomalies hint at a primordial preference, a fingerprint from the first moments of time. This connection between the very old and the relatively recent universe is staggering. It suggests that the seeds for the mysterious alignments were not planted by dark matter or modified gravity acting later, but were encoded in the initial conditions of everything. Think of it like a potter giving a lump of clay one initial, gentle twist. As the wheel spins for eons, that single motion can define the final shape of the entire vessel. The axis of evil could be that first, fundamental twist. This idea forces us to look beyond classical physics and into the quantum realm. In the first fleeting instance after the Big Bang, the universe was a seething sea of quantum fluctuations. What if one of those random fluctuations was not entirely random? What if a single quantum event, magnified to cosmic proportions during a period of rapid inflation, imprinted a directional preference on the entire observable universe? This would mean the alignments we struggle to explain are not a flaw in our current laws, but a fossilized echo of the universe's quantum birth. The search for understanding now pulls us backward in time, from the sprawling star clusters of today to the very first trillionth of a second, where the rules of reality as we know them may have been written with a slight, mysterious bias. The universe's first moments were a storm of pure potential. In the inflationary epoch, a fraction of a second after the Big Bang, all of space underwent an exponential growth spurt, stretching from a subatomic speck to a vast cosmic volume. Within this furious expansion, the fabric of reality itself was jittering with quantum fluctuations. These are tiny, random variations in energy, virtual particles flickering in and out of existence. As space inflated, these microscopic ripples were stretched to astronomical proportions, frozen into the fabric of spacetime as faint overdensities and underdensities. These became the primordial seeds, the gravitational blueprints for every galaxy, star, and cluster we see today. But the mystery of the alignments forces us to ask a deeper question. What if those initial quantum jitters were not perfectly random? Our standard model assumes they were, leading to a universe with no preferred direction. Yet the coordinated spins we observe suggest the dice may have been loaded from the start. Theoretical physicist Dr. Andre Lind has explored how certain specialized models of inflation, involving what are known as non-standard scalar fields, could generate these kinds of correlated initial conditions. Imagine these fields not as a uniform energy soup, but as a fluid with a subtle current. As inflation stretched this fluid, it could have imprinted a faint directional preference onto those quantum seeds, a kind of cosmic grain that was woven into the universe's very foundation. This means the large-scale structure we see today, with its strangely aligned clusters, might have been programmed with a bias from its very first moments. The spin of a single galaxy, then, is not just a local event. It is the final expression of a quantum instruction set written at the dawn of time, a ripple from the first storm that still guides the cosmic dance. This local coordination of galaxy spins offers a smaller, more intimate view of the cosmic mystery. While the grand alignments span billions of light years, the dance is also happening in our own galactic neighborhood. Within dense clusters, astronomers have found that spiral galaxies, those majestic pinwheels of stars, often show a curious kinship in their spins. Their rotational axes, the invisible lines around which they turn, frequently point in similar directions. It is as if you dropped a handful of leaves into a swirling whirlpool. Each leaf is its own entity, yet they all begin to circulate together, caught in the same overarching flow. This is the power of the local cosmic environment. To uncover this pattern, researchers like Dr. Jun-Hyop Lee analyze vast surveys of the sky, meticulously measuring the tilt and orientation of thousands of spiral galaxies. The statistical evidence they gather is clear. Galaxies that are neighbors within a cluster are not spinning randomly. They show a coherence, a subtle but definite preference for alignment. Dr. Lee explains that this shared spin direction suggests the galaxies inherited their angular momentum from the tidal torques of the cosmic web. What does that mean in simpler terms? As these galaxies formed billions of years ago, they did not collapse in isolation. They were born within the immense, flowing rivers of dark matter that make up the cosmic web. The gravitational pull and shear from these vast, streaming structures gave the infant galaxies a gentle, collective twist, a spin that they have carried with them ever since. This local phenomenon acts as a crucial bridge in our understanding. It connects the behavior of a single galaxy directly to the architecture of the entire universe. The same forces that gently align galaxies within a cluster are likely the very same forces, operating on a far grander scale, that create the mysterious alignments between clusters separated by unimaginable voids. By studying this local whirlpool, we gain a key to understanding the entire ocean. So, what is the true nature of this cosmic web that orchestrates the spin of galaxies near and far? This intricate cosmic web is the ultimate stage for the universe's grand design. It is not a chaotic splatter of galaxies, but a highly structured network, a vast architecture of dark matter and luminous matter woven together. This web consists of three primary elements. Dense clusters act as bustling metropolitan hubs where thousands of galaxies crowd together. Immense, nearly empty voids stretch between them like silent, cosmic deserts. And connecting everything are the filaments, long, thread-like structures that serve as the universe's gravitational highways. It is within these filaments that the mystery of cosmic alignment finds its most potent expression. Galaxies and entire clusters are funneled along these dark rivers, their motions and rotations guided by the deep gravitational currents. Imagine cars streaming down a multi-lane freeway. While each vehicle has its own engine and driver, its overall direction of travel is dictated by the road itself. In a similar way, a galaxy's spin can become aligned with the filament it calls home, a subtle coordination imposed by the largest structures in existence. Sophisticated computer simulations of the universe's evolution reveal this process in stunning detail. They show how dark matter halos, the invisible gravitational pits that host visible galaxies, often have their spins correlated with the orientation of their filament. This is not a perfect lockstep alignment, but a strong statistical tendency, a gentle nudge from the cosmos that says, spin this way. The cosmic web, therefore, is not a passive backdrop. It is an active director, a choreographer that orchestrates the orientations of countless structures across space and time. This understanding transforms the mysterious alignments from a baffling anomaly into a natural consequence of the universe's architecture. It shows us that the hidden patterns are written into the very blueprint of reality. To move from these theoretical simulations to confirming this grand design in our real universe requires a new way of seeing, a technological leap that allows us to map the invisible threads connecting the cosmos. Detecting these faint cosmic whispers across billions of light years is a monumental task of observation and deduction. Our eyes on the sky, telescopes like Hubble and the Very Large Telescope, conduct wide-field surveys, meticulously mapping the positions and tilts of millions of galaxies. They do not simply take pretty pictures, they gather precise data on a galactic scale. To uncover the subtle alignments, astronomers measure what is known as the position angle, essentially determining which way a spiral galaxy is pointing on the sky. They analyze the polarization of light, which can reveal the orientation of dust and magnetic fields within a galaxy. Then, they apply powerful statistical tools like correlation functions to vast datasets. These mathematical probes sift through the apparent randomness, searching for the hidden signal of coordinated spins. As Dr. Michelle Collins notes, without this combination of advanced instrumentation and sophisticated data analysis, these subtle correlations would simply remain lost in the noise. The hunt for cosmic alignment has even enlisted the help of the public through ambitious citizen science projects. Online platforms allow volunteers around the world to visually classify galaxy shapes, their collective human pattern recognition helping to train algorithms and confirm what machines might initially miss. This collaborative effort between human curiosity and technological prowess is pushing the boundaries of what we can see. Each new telescope, like the upcoming James Webb Space Telescope, offers a deeper, sharper view, enhancing our ability to probe these mysteries. With every technological leap, we gather more pieces of the puzzle, and one of the most intriguing pieces points toward a force that permeates the cosmos itself. The possibility that cosmic magnetism is gently guiding these vast structures into alignment. The universe is not only shaped by gravity, but also by invisible magnetic threads woven through the cosmos. These large-scale magnetic fields are incredibly faint, yet they stretch between galaxies and clusters, creating a subtle force that could guide the formation of cosmic structures. Think of the early universe as a vast, dark ocean. As the first clouds of ionized gas began to collapse under gravity, these pervasive magnetic fields would have acted like gentle currents, influencing the direction of the collapse and potentially imparting a shared spin to the infant galaxies that formed within them. This is not a dominant force, but a subtle nudge, a whisper of direction in the chaotic dawn of time. Astrophysicist Dr. Franco Vazza describes these fields as cosmic threads that could weave patterns into the distribution of matter. The challenge is proving they exist on such immense scales. We cannot see them directly, but we can detect their ghostly presence through their effects. When high-energy electrons spiral along a magnetic field line, they emit a specific type of light called synchrotron radiation. We can also measure how these fields twist the polarization of light from distant quasars, a phenomenon known as Faraday rotation. These techniques provide compelling, though indirect, evidence that a magnetic tapestry is real. The idea that primordial magnetic fields, relics from the universe's earliest moments, could have guided galactic spins adds a fascinating layer to our mystery. It suggests an intricate interplay where gravity builds the cosmic scaffold and magnetism fine-tunes the details of the dance. This multifaceted origin, combining dark matter, modified gravity, and now cosmic magnetism, points toward a universe of profound interconnectedness. But if all these forces are conspiring to create a pattern, what does that pattern ultimately reveal about the shape of reality itself? The universe might possess a fundamental geometry, a subtle shape written into its fabric that we are only now beginning to perceive. This is the profound implication of the star cluster alignments, suggesting our cosmos is not perfectly uniform in all directions. Instead, it may exhibit a large-scale anisotropy, a scientific term meaning its properties change depending on which way you look. Imagine holding a perfectly smooth, round ball. This represents our traditional view of an isotropic universe. Now imagine that ball has a faint, almost imperceptible grain, like wood, running through it in one particular direction. This grain represents a cosmic handedness, a preferred axis woven into the very nature of space and time. The coordinated spins of distant clusters could be tracing out this hidden grain, pointing toward a universal north that should not exist. This idea directly confronts the cosmological principle, the long-held assumption that the universe has no special place or direction. Cosmologist Dr. Andrew Liddell suggests that if the universe has a preferred direction, it would revolutionize our understanding of its origin and evolution. Such a geometric flaw in cosmic symmetry forces us back to the drawing board. How could this happen? Some theoretical models propose that the rapid inflationary expansion of the early universe was not perfectly even. It might have stretched space more in one direction than in others, imprinting a faint directional preference that persists to this day. This primordial stretching could be the reason why galaxy clusters billions of light-years apart seem to remember a common orientation. Their alignment is a fossilized echo of that first, asymmetrical growth spurt. This radical notion even opens a door to multiverse theories. Our anisotropic universe, with its specific handedness, could be just one bubble in a vast cosmic foam, each with its own unique geometry and physical laws. To comprehend such an abstract concept, scientists rely on sophisticated computer simulations. These digital universes allow researchers to test different geometric models, watching as virtual galaxies form and evolve within a cosmos that has a built-in preferred direction. The goal is to see if these simulated universes can reproduce the strange alignments we observe in our own, turning a philosophical possibility into a testable, visual reality. This geometric perspective invites us to see the cosmos not as a formless void, but as a structured entity with a hidden shape, a shape whose contours we are only just beginning to trace with the most sensitive instruments ever built. These digital universes are born from lines of code and mathematical rules, allowing us to ask the cosmos, what if? Scientists run sophisticated N-body simulations, modeling the gravitational dance of millions, even billions, of virtual particles. These are not simple animations, but entire synthetic universes evolving over billions of simulated years. Programs like the landmark Millennium simulation recreate the growth of cosmic structure from the smooth soup of the early universe to the intricate web of filaments and clusters we see today. The true power of these models emerges when the mysterious alignments appear within them. When virtual galaxy clusters in a computer show coordinated spins, researchers can rewind the simulation and trace the origin of that pattern back to a specific physical process. They can see the exact moment when a dark matter filament imparted a gentle twist to a forming cluster. Dr. Volker Springel, a pioneer in this field, explains that simulations allow us to play with different physics and see if we can reproduce the observed patterns. This digital experimentation is crucial for distinguishing between competing theories. Does the alignment signal vanish if we remove dark matter from the model? Does it strengthen if we switch the rules to a modified gravity framework? The success or failure of these virtual worlds in matching our real observational data directly guides the development of new theories. Each simulation is a grand thought experiment, a test of our understanding against the ultimate benchmark of reality. These virtual experiments illuminate real-world mysteries by letting us run the universe again and again, each time with a different set of rules, pointing decisively toward the future observations that will finally separate cosmic fact from fiction. The next decade of astronomy will be defined by an unprecedented leap in our vision. A new generation of observatories, both in space and on the ground, is poised to transform these faint cosmic whispers into a clear, measurable signal. The European Space Agency's Euclid satellite is already charting the dark universe in stunning detail, while the upcoming Nancy Grace Roman Space Telescope will perform galactic archaeology on a colossal scale. On Earth, the square-kilometer array will use a forest of radio antennas to listen to the cosmos, mapping the distribution of hydrogen gas across billions of light-years. Together, these missions will produce a census of the sky so vast and precise that it will allow us to test the alignment phenomenon with a statistical power we can only dream of today. Dr. Jason Rhodes, a project scientist for Euclid, captures the anticipation, stating, "We will measure the shapes and orientations of billions of galaxies, providing a definitive test for large-scale correlations." This is not merely about collecting more data. It is about asking the universe a direct question and receiving an unambiguous answer. These surveys aim to do three things: confirm the reality of the alignments beyond any reasonable doubt, measure their exact strength and how they change across different cosmic epochs, and crucially, pinpoint their underlying cause. Is the signal strongest along the filaments of the cosmic web, pointing to dark matter as the architect. Does it match the predictions of modified gravity models, or does it correlate with the ancient axis seen in the cosmic microwave background? The answers are within reach. The collective excitement within the global astronomical community is a tangible force, a shared understanding that we are standing on the precipice of a potential revolution. These collaborative endeavors, uniting scientists and institutions across continents, highlight a profound truth. The quest to understand our place in the cosmos is a human journey, one that transcends borders and reminds us of the power of shared curiosity. What will the universe reveal when we finally learn to see it in its entirety? Unraveling the cosmos requires more than powerful telescopes. It demands a united front of human intellect. This grand endeavor is a symphony of global collaboration, where projects like the Sloan Digital Sky Survey and the Dark Energy Survey bring together hundreds of scientists from dozens of nations. These are not merely data collection exercises, they are monumental feats of international cooperation, pooling financial resources, specialized expertise, and computational power to confront mysteries that no single country or institution could solve alone. As theoretical astrophysicist Dr. Priyamvada Natarajan observes, cosmology is a team sport. We need diverse perspectives to interpret complex phenomena. This diversity is its greatest strength. A theorist in India might see a pattern in the data that a telescope operator in Chile misses, while a data analyst in the United States develops a new algorithm to test both of their ideas. This collective scrutiny, where every finding is examined from countless cultural and scientific angles, forges a more robust and reliable path to the truth. It accelerates discovery by preventing individual blind spots from becoming dead ends. This spirit of shared pursuit highlights a beautiful truth about science. It is a human journey that transcends political borders in the quest for fundamental knowledge. And this journey does not end in the halls of academia. The vast datasets from these collaborations are often made public, inviting citizen scientists and amateur astronomers from around the world to participate in the process of discovery. This broad engagement ensures that the profound breakthroughs about our place in the universe are understood and appreciated by everyone, making the cosmos a shared inheritance for all of humanity. This cosmic mystery reaches far beyond professional observatories, touching a deep human desire to understand the stars. Online platforms like Zooniverse have unlocked the universe for everyone, transforming your computer screen into a personal portal for discovery. Here, volunteers from all walks of life can sift through millions of real galaxy images, helping scientists classify shapes and orientations. It is a global, digital star party where a teacher in Brazil, a retiree in Japan, and a student in Canada can all work side by side to identify the very patterns that might reveal the cosmos's hidden structure. This is the true democratization of science, where curiosity is the only credential required. Even amateur astronomers with backyard telescopes contribute valuable data, their meticulous sketches and photographs of galaxy tilts adding to the collective pool of knowledge. This public engagement does more than just accelerate research. It builds a bridge between the abstract world of theoretical physics and our innate sense of wonder. When you personally help classify a distant spiral galaxy, its story becomes a small part of your own. This shared journey of discovery inspires future scientists and reminds us that the quest to comprehend the universe is a fundamental human endeavor. It is a process driven by collective curiosity, a force that propels us to ask the next, most profound question. What does it mean for us if the universe is not a chaotic accident, but a place with a subtle, woven-in pattern? A universe governed by pure chance would look nothing like this. The silent, statistical coordination of star clusters across billions of light years points toward a cosmos with a deep-seated order, a fundamental architecture that resists randomness. This discovery forces a profound philosophical shift, challenging the long-held assumption that our universe is a grand, accidental expanse. Instead, we are confronted with the possibility of a reality woven with intrinsic patterns, a cosmic tapestry where every thread, no matter how distant, is part of a coherent whole. Philosopher of science Dr. Tim Maudlin suggests that such large-scale structures compel us to reconsider the very nature of physical law and causality. Could the connections we see be the result of a deeper, more intricate set of rules that operate across the entirety of spacetime? This is not necessarily an argument for a conscious designer, but rather for a universe whose natural laws are far more complex and interconnected than our current models allow. It hints at a cosmos where the concept of separate, isolated events may be an illusion, and where influence and correlation are baked into the fabric of existence. This moves the discussion from pure astrophysics into the realm of metaphysics, asking us what it means to live in a universe that might possess a form of cosmic destiny, a predetermined lean toward order. For humanity, this changes everything about our place in the cosmos. Are we simply random inhabitants on a random planet, or are we participants in a universe that inherently tends toward structure and perhaps even complexity? The alignments suggest that the universe has a story, a narrative arc written into its very foundations. This philosophical dimension is not an endpoint, but a gateway, compelling us to search for the new physical principles that must underpin such a deeply ordered reality. These unexpected patterns in the cosmos are more than just a puzzle. They are a potential gateway to an entirely new kind of physics. What we are witnessing could be the first observational evidence of realms beyond our current understanding, pointing toward phenomena that lie outside the standard model of particle physics, and even our cherished theory of general relativity. The subtle coordination of star clusters might be a trace, a faint signature, left by exotic fields we have yet to name, or the gravitational tug of hidden higher dimensions. Theoretical physicist Dr. Lisa Randall has extensively explored how such extra dimensions, curled up at scales impossibly small, could nevertheless influence the large-scale structure of the universe we see. The gravitational force might be leaking between these dimensions, creating subtle correlations across vast cosmic distances that appear to us as these mysterious alignments. This line of thinking opens the door to even more staggering possibilities, such as interactions with other universes within a vast multiverse. Perhaps our universe is not entirely isolated, but is gently brushing against others in the cosmic foam, and these alignments are the gravitational fingerprints of that contact. The ultimate prize in this search is a theory of quantum gravity, a way to unite the world of the very small with the world of the very large. The alignments could be the crucial observational clue that guides us toward this unified theory, while also shedding light on the true nature of dark energy, the mysterious force accelerating the universe's expansion. This pursuit is not merely about explaining one single anomaly. It is about expanding the entire framework of physical law, rewriting the rules that govern reality itself. The stakes could not be higher, for solving this cosmic puzzle would not just answer a question, it would redefine the very nature of the questions we are able to ask. Science thrives on healthy skepticism, and this cosmic mystery is no exception. A chorus of respected voices urges caution, reminding us that extraordinary claims demand an even higher standard of proof. The central challenge lies in distinguishing a true signal from the immense background noise of the universe, where imperfections in our data can easily create the illusion of a pattern. Dr. David Hogg offers a crucial perspective, stating that extraordinary claims require extraordinary evidence, and we must rule out all mundane explanations first. This is the essential, methodical work of science. For instance, a phenomenon known as selection bias could be at play. If our telescopes only survey certain patches of the sky, or if our data processing software inadvertently favors galaxies tilted in a particular way, we might be measuring an artifact of our own methods rather than a property of the cosmos. Similarly, what appears as a statistically significant alignment across billions of light years might simply be a random fluctuation, a temporary clustering in the data that will vanish as we gather more observations. There are also known astrophysical processes that could create local coordination without any need for new physics. Galactic cannibalism, where a large galaxy consumes a smaller neighbor, or major mergers between galaxies, can dramatically reorient their spin axes. In a dense cluster, such violent interactions could lead to a group of galaxies sharing a similar orientation, simply because they have all been shaped by the same local gravitational turmoil. These are the mundane, well-understood explanations that must be conclusively ruled out before we can confidently point toward dark matter, modified gravity, or primordial quantum fields. This rigorous process of challenge and verification is not a weakness, but the very engine of scientific progress. It ensures that when we finally do accept a revolutionary conclusion, it is built upon a foundation of evidence that can withstand the most intense scrutiny. This critical perspective sharpens the question, pushing us to look even deeper into the data to see if the alignments are a fleeting illusion or a profound clue to the universe's enduring structure, a structure that may ultimately dictate its final destiny. These vast cosmic alignments may do more than reveal our past. They might foretell our final destiny. The subtle grain in the universe's fabric could influence its ultimate fate, shaping how the cosmic story ends billions of years from now. In highly speculative models, a persistent preferred direction might subtly alter the behavior of dark energy, the mysterious force accelerating the expansion of space. Imagine dark energy not as a perfectly uniform pressure, but as a force with a faint texture, stronger in some directions than others. This anisotropy could lead to an uneven expansion, potentially steering the cosmos toward a specific endgame. Cosmologist Dr. Paul Steinhardt explores how such anisotropic initial conditions, if they persisted, could lead to futures far different from the standard predictions. Instead of a gradual heat death where the universe cools into emptiness, an anisotropic cosmos might be destined for a more dramatic finale. One possibility is a Big Rip scenario, but with a twist. If dark energy's strength is linked to the cosmic grain, its increasing dominance could eventually tear apart galaxy clusters, stars, and even space-time itself in a directional manner, a rending of the cosmic fabric along its hidden seams. Alternatively, these primordial flaws could be the key to a cyclic universe. If the alignments are echoes of a previous cosmic cycle, they might provide the blueprint for a future contraction and rebirth, a perpetual cosmic heartbeat guided by its ingrained patterns. While these ideas remain at the frontier of theoretical physics, they highlight a profound truth. The same initial seeds that shaped the first galaxies are still whispering to us today, and their message contains clues not just about where we came from, but about where we are ultimately headed. Understanding these patterns is not merely an archaeological dig into the past. It is an act of cosmic forecasting. To decode this message fully requires us to look beyond a single field of science, uniting cosmology with disciplines that study complexity and pattern on every scale. This cosmic puzzle is too vast for any single field of science to solve alone. The search for answers has sparked a remarkable convergence of disciplines, each bringing its own unique lens to the mystery. Cosmologists chart the large-scale structure, while particle physicists probe the quantum rules that govern the universe's first moments. To understand how alignments can span such immense distances, researchers even turn to the principles of fluid dynamics, modeling the cosmic web as a flowing river of dark matter, its currents gently guiding the spin of galaxies. The mathematical language used to describe these flows comes from vector calculus and topology. fields that study the properties of shapes and spaces. These tools help scientists model how a subtle directional preference could be preserved across billions of light years, tracing a coherent pattern through the chaos. This integrative effort pushes into the most theoretical realms, where collaborations between astrophysicists and string theorists, like those involving Dr. Brian Greene, attempt to bridge the greatest divide in physics. They work to connect the infinitesimally small world of quantum strings with the astronomically large scale of galactic alignments, exploring how hidden dimensions could influence the cosmos we see. This multidisciplinary dialogue is not just helpful, it is essential. Breakthroughs rarely happen in isolated silos. They emerge at the vibrant intersections between fields, where a tool from one specialty can unlock a stubborn problem in another. By weaving together these diverse threads of knowledge, scientists construct a far more comprehensive and resilient model of reality. This collaborative spirit, this shared language of curiosity, is the engine of modern discovery. It also highlights a critical final piece of the puzzle: the need to translate these profoundly complex ideas into a story that everyone can understand and share. A distant galaxy's silent spin becomes more than data when a skilled storyteller gives it a voice. This is the vital art of science communication, the bridge that connects the esoteric language of cosmology to the public's innate sense of wonder. Scientists like Dr. Neil deGrasse Tyson excel at this, translating the mathematics of cosmic alignments into powerful analogies we can all grasp. They might compare the coordinated spin of galaxy clusters to a vast flock of birds turning in unison, or describe the cosmic web as a colossal neural network, with galaxies firing like thoughts along its filaments. These are not mere simplifications, they are essential tools for understanding. By transforming abstract data into relatable narratives, communicators perform a crucial service. They dispel myths and prevent the spread of misinformation, fostering a public that is not only informed but also supportive of the ambitious research that drives discovery forward. This clarity also fuels collaboration, as a physicist must be able to explain their findings to a biologist or a computer scientist for true interdisciplinary breakthroughs to occur. When a complex idea is rendered with clarity and passion, it ceases to be an intimidating equation and becomes an invitation. It sparks curiosity in a student, provides perspective for a philosopher, and reminds us all that the universe's grandest mysteries are, in fact, a shared human inheritance. This emphasis on outreach ensures that the profound implications of star cluster alignments resonate far beyond lecture halls, transforming every new answer into a fresh question that beckons us all to look up and wonder what comes next. The precise mechanism weaving these cosmic patterns remains one of the greatest unsolved puzzles. Is the force behind these alignments a local phenomenon, confined to specific superclusters and filaments, or is it a truly universal feature, a fundamental property of spacetime itself? The answer would reshape our entire cosmic map. Furthermore, how do these coordinated spins relate to other cosmological anomalies, like the mysterious cold spot in the cosmic microwave background or the puzzling Hubble tension, which suggests a disagreement about the universe's expansion rate? Are these all separate issues, or could they be threads leading back to a single, deeper flaw in our understanding? Future research holds the key to another critical distinction, determining if the alignments we see are a temporary phase in the universe's evolution or a permanent fixture of its architecture. As renowned astronomer Dr. Sandra Faber observes, every time we think we have a handle on the universe, it throws us a curveball. This sentiment captures the very heart of the scientific endeavor. These open questions are not a sign of failure, but the engine of discovery. They are what drive the development of ever more powerful telescopes and more sophisticated theoretical models. The persistence of such profound mystery ensures that cosmology remains a dynamic, living field, forever pushing at the boundaries of the known. It is a powerful reminder that our current knowledge, for all its sophistication, is merely the tip of a vast and uncharted iceberg. The Planck satellite's mission was to capture the universe's first portrait with a clarity never before achieved. Its map of the cosmic microwave background is our most detailed baby picture of the cosmos, a snapshot of the universe when it was just 380,000 years old. While it largely confirmed the standard model of cosmology, it also revealed faint, puzzling blemishes on this ancient canvas. These are the large-scale anomalies, subtle asymmetries that should not exist in a perfectly uniform universe. One of the most significant is found in the low multipole moments, which describe the very largest ripples in the early cosmos. Think of these as the fundamental background hum of the universe. Planck's data showed that this hum is not the same in all directions. There is a hemispherical asymmetry, a kind of power imbalance where one half of the sky shows slightly stronger temperature fluctuations than the other. It is as if the universe was born with one hemisphere just a little bit more active than the other. This discovery provides a critical, indirect link to the alignments we see today. The same primordial conditions that created this lopsided infant universe could have also imprinted a directional preference on the swirling gas that would one day form galaxy clusters. Analysis of the Planck data by teams like the one led by Dr. George F. Stetheu has meticulously traced these correlations. They have explored how the axis defined by these CMB asymmetries might align with the preferred directions we now observe in the spin of modern galactic structures. This is not a direct, one-to-one match, but a compelling statistical hint that the universe's first moments and its current architecture are deeply connected. Planck's legacy, therefore, is not a set of final answers, but a far richer and more complex picture of cosmic genesis. It demonstrates a powerful convergence of evidence, where the oldest light we can see and the newest galactic surveys are both telling us the same story, a story of a cosmos with a hidden grain. This fuels the ongoing debate, pushing investigators to search for the physical mechanism that could have woven this coherence from the first instant into the present day. The vast resources dedicated to studying the cosmos inevitably raise a profound question. How do we justify peering into deep space when our own world faces such pressing challenges? This is not a simple dilemma, but a complex ethical conversation about the value of knowledge itself. Ethicists like Dr. Catherine Denning remind us that the drive to understand the universe is a fundamental part of our cultural and intellectual heritage. It is a human impulse as ancient as the first stories told around a fire, a quest to find our place in the grand narrative of existence. While funding for telescopes and space missions is substantial, it often yields returns that touch our daily lives in unexpected ways. The technology developed to peer at distant galaxies spins off into medical imaging, weather forecasting, and global communication networks. These innovations are not the primary goal of cosmic research, but they are a powerful and recurring side effect of pushing technological boundaries. Furthermore, this pursuit cultivates a priceless global perspective. A photograph of Earth as a pale blue dot, suspended in the void, carries an emotional weight that transcends borders. It fosters a sense of shared destiny, reminding us that we are all crew members on a single, fragile vessel traveling through the cosmos. This perspective can inspire international cooperation and a deeper commitment to stewardship. The dialogue is not about choosing between Earth and the stars, but about recognizing that science serves humanity's broader well-being in multiple ways. It provides practical tools, yes, but it also nourishes our spirit, fuels our imagination, and unites us under a common, starry sky. This balance between immediate needs and transcendent curiosity is a testament to our multifaceted nature, proving that we are a species that must both mend its home and dream of what lies beyond. Our journey through these silent, spinning giants reveals a cosmos far stranger than we ever anticipated. This is not a story with a tidy ending, but an ongoing investigation that stretches from the first glimmers on photographic plates to the most radical theories of quantum gravity. We have watched as a faint statistical hint blossomed into a fundamental challenge, forcing us to question the very laws we thought governed reality. The cosmological principle, dark matter, even Einstein's theory of gravity, all have been put under the microscope by this single, persistent mystery. The profound takeaway is not a specific answer, but a new perspective on the universe itself. It appears to be a place of deep, hidden order, where structures separated by billions of light years are subtly linked, whispering to each other across the void. These are not random islands in a dark sea, but part of a coherent, interconnected whole. The late astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. That sense of anticipation now pulses through this entire field of study. The alignments are a clue, a cosmic signpost pointing toward that incredible something. So the next time you find yourself beneath a clear night sky, look up. Let your eyes wander across the tapestry of stars, and remember that what you are seeing is not a random scattering. It is a grand, structured, and still mysterious design, one that we are only just beginning to decode. We would love to hear what this cosmic mystery makes you wonder about. Share your thoughts in the comments, and if you are eager for more journeys to the edge of understanding, subscribe for our next exploration. The search is far from over, and every new observation brings us one step closer to comprehending our place within this astonishing cosmos.